Welcome to another one of Mr. Newman's flip lecture videos. As always, before we get this video started, let's start up with the warm-up question. Warm-up question: what do all these things have in common? Take a minute, pause the video here, analyze those pictures, come up with the answer to this question. When you got it, move on. So answer, they're all waves. If you didn't get the answer, go back, look at the pictures again, see if you can come up with why that is. The answer is they're all waves, just like those lines down bottom. They're all wiggly and moving. They're waves, which is the topic of today's video. Mr. Newnam's flip lecture videos, physical science. Topic: wave properties. Unit: waves, theme, music, and rock and roll. Let's talk science. Here are the standards for this video. Take a minute, pause it, go through these at your own time, and then move on. Here are the objectives for this video. Again, pause the video here, read through these videos, read through the objectives, and come back at the end of the video. Make sure you can answer all these objectives and you're able to do all these things. By now you're probably wondering, what is a wave? The scientific definition is: a wave is a repeating disturbance or movement that transfers energy through matter or space. The most important part of this definition is that waves transfer energy. Waves are a transfer of energy. So the picture above, you have energy in your hand. As you shake the rope, it goes from one end of the rope down to the spring and then back. The energy is transferred along the rope. The rope itself only moves a little bit up and down. Waves transport energy. Energy traveling, not the rope itself. Waves and mediums. The medium of a wave is the material the wave travels through. It can be solid, liquid, gas, doesn't matter. The medium affects the wave's speed. Waves travel at different speeds depending on what they're going through. It's going to slow them down or speed them up. Mechanical waves are classified into one of two types, according to the direction that they move in relationship to the medium. The picture to the right, that's a psychic medium. They call her that because the psychic powers travel through her, so she's the wave of the psychic powers. Waves and matter. All waves transport energy. Some waves transport energy through material. Other waves, such as light, do not need material to transport energy through. Light can travel through space. Light's a wave. It doesn't require something to travel through. Mechanical waves, which we're talking about, need something to travel through. In the picture below, the ocean waves, the wave is the medium, the water, the ocean. That's what the wave travels through. Two types of mechanical wave. There's transverse waves and compressional waves. Transverse waves, the medium moves back and forth at right angles to the direction that the wave is traveling. They move in opposite directions, 90 degrees from each other. Compressional waves, the medium moves back and forth along the same direction that the wave is traveling. Transverse waves. The picture above is a transverse wave. The people are doing the wave. Their energy of excitement is going across the screen from left to right. The wave's traveling that way, but the people are only moving up and down. They're moving at right angles to each other. Physically, they're moving up and down, but the energy is going carried across. Compressional waves, the medium moves the same direction. The springs is compressing. It's moving from left to right. The wave's moving to left to right. The slinky is vibrating left and right. They're the same direction. It's compressional waves move the same direction as the medium they travel through. Classify the following waves as compressional or transverse. Pause the video here, look at these, see if you can classify which one's transverse, which one's compressional. Bring your answer to class with you tomorrow. When you're done, move on. Transverse and compressional waves sometimes mix. Ocean waves in the ocean are a mixture of transverse and compressional waves. The water moves the same direction and opposite at the same time, gets these nice surfing waves that people ride. Parts of the wave. The wave has four basic parts: a crest, a trough, an amplitude, a wavelength. Crest and trough. So the crests are the peaks of the wave, the top high parts, where the particle the wave moves through, the medium, is disturbed the most upwards away from where it started. The trough is the bottom part of the wave. That's where the particle is moved the most down away from its started of. So trough, think of like do not have high points or low points. They have compressed parts and they have stretched out parts. The compressed parts are called compressions, and the stretched out parts are called rearfractions. Amplitude. The amplitude is the maximum distance the wave moves the medium away from its normal resting position. So the top of the crest, that's the amplitude. The bottom of the trough, that's the amplitude. The resting position, where the particle would normally be before the energy of the wave hit it. How it moves, the maximum moves up or down, is the amplitude. The higher it moves, the higher the amplitude, the higher the energy. The less it moves, the lower the energy. Wavelength. The wavelength of the wave is the distance between one point on the wave and the nearest point just like it. So pick a point, travel along the wave to the next point moving the same direction at the same time in the same spot. That's one wavelength. Easiest way to find the wavelength is to measure the distance between the crests or the distance between the troughs. That's one full wavelength because both of those pieces are exactly alike. The shorter wavelengths have more energy. The longer wavelengths have less energy. Wavelengths is measured in meters because it's the distance, it's the length, and it's given the symbol lambda, which is like a funky looking X. Before moving on, pause the video here. How many wavelengths are on this wave so you can identify them? Start with one point and find many other points that are exactly like it, move in the same direction at the same place. When you're done, move on, unpause the video and move on to the next slide for your answer. There's 3 wavelengths there. Starting at one red spot to the next red spot, that's one wave. From there, that second one spot is the along that distance. If you didn't get that answer, go back and review. If you did, move on. This wave, each wavelength goes between 2 red spots. If you didn't get that answer, go back and review. If you did, move on. Frequency. The frequency of a wave is the number of wavelength of a wave that passes by a fixed point in 1 second. Frequency is measured in hertz. A frequency of 1 hertz means that one wavelength passes by a certain spot every second. The higher the frequency of a wave, the more energy the wave has. The higher the frequency, the shorter the wavelength. It doesn't take as long to complete. Which of these has a higher frequency? Take a minute, answer this question. When you're done, you think you got an answer, move on. So the top kangaroo produces waves that are higher in frequency. He goes faster. He does more jumps in the same amount of time. He has more energy. The bottom kangaroo has shorter or longer wavelengths. He doesn't bounce as much. He's got less energy. Period. The period of a wave is the amount of time the wave takes to go through one wavelength or one wave cycle. Waves with short periods have high frequencies and high energy. Waves with long periods have low frequencies and low energies. That wave is going through one wavelength. The period's changing in that picture. Starts off short periods, high frequency, and it gets longer every time the picture replays. Frequency, wavelength, period, and energy. Frequency increases, wavelength decreases. Frequency increases, period decreases. Frequency increases, energy increases, wavelength increases, period increases, wavelength increases, wavelength decreases, energy increases, wavelength decreases. Pause the video, take a moment to answer the following question. Be prepared to turn in and discuss this question or similar ones in class tomorrow. If you were to increase the wavelength of a wave, what do you do to the wave's frequency? How does this change the wave's period? And how did this change the wave's energy? How do you think this would change the wave's amplitude? Answer that question, bring it to class tomorrow. How does this relate to music and to Elvis? Where's the music at? That's our theme. Sound is a wave. When listening to music, we hear different sounds. Sound's a wave. Sound is the energy of a wave that travels through the air. The medium of a sound wave is the air particles move and vibrate as the sound wave travels through the air. Music is a combination or collection of different sound waves. Objects that produce sound vibrate. Objects that produce sound vibrate in waves. These vibrating waves and objects vibrate the air around them. The vibrating air waves have the same frequency as the vibrating object that create them. Different sounds are produced by vibrating objects that are vibrating in different frequencies. Different sounds are made from sound waves with different frequencies, wavelengths, periods, amplitudes, and energies. A look to the future. How will we analyze sound waves in this class? What are we going to do for our unit? In this class this week, be prepared to build a sample string instrument, measure and record the wavelength and frequencies of waves produced by strings on your instrument, analyze the relationship between wavelengths on the string and frequencies produced, analyze the relationship for other instruments, including instruments used by Elvis, analyze and study sounds created in Elvis songs to determine wavelengths, frequencies, and wave speeds on the strings of the guitar, research the guitar and similar ones used by Elvis that are being sold at a local music store. Calculate the speed of the waves in the string on the guitar when it's used to play chords in the song Elvis' song Hound Dog. Use the research data to help the music store market the guitar that you're researching. When you've got all that, you're going to present this data to employees at the music. Thanks for watching. Thank you very much.